So welcome back. In this video, we'll be talking about the unit operations for coagulation practices. The first one is the rapid mixing unit, which we are calling as a flash mixing chamber or simply flash mixer. So this is a flash mixer. You can see here in this model picture. This is what you call a tank. Now this is the water, and where you're having a shaft is there, and impeller blades are there, and they are rotating using a motor at the top. Water will be entering from one side and leaving in the opposite direction, to the next treatment unit. Then we can see this is the diameter of impeller blades, so we denote it with small d, and the diameter of the tank, capital D, and this is the water depth in the tank, say capital H. What you notice here is the depth of the tank is more than the diameter or width of the tank. And the right side, you can see this is a tank used as a flash mixer. The cement tank is used, circular tank. You can see on top there is a motor mounted on a small platform. There you can see the inside, you can put water, and then you can see a shaft and which is inserted with the blades at the bottom, right? So the most important parameters in the design are first one is the average velocity gradient, which we normally denote as G, average velocity gradient or mean velocity gradient. What does it indicate? When you're rotating this shaft with impeller in the tank, because of the sweeping area of the blades, the higher velocity will be imparted at the tip or near to the blades, and slightly lesser velocity is imparted, which is slightly above, and going slightly higher, marginally lesser velocities are there at different points. What we are saying is the average velocity in the entire depth of the tank we are going to consider. So what this mean is the average velocity is nothing but meter per second. That is the overall velocity in the entire depth of the tank. So meters. So this is nothing but we are having per second. And the power imparted to the tank here per rotation, we are calculating using G square V mu. G square V into mu. So mu is the absolute viscosity, G is what we have discussed here, V is the volume of the tank, and volume of the tank we will find out from the fundamentals of fluid mechanics, multiplying volumetric flow rate, multiply with the contact time in the tank. The contact time will be around 20 to 60 seconds, and within that we will assume and then we will calculate the volume, right? The other important thing is the ratio of the diameter of impeller to the diameter of the tank. So D by D, you can see here, which is around 20 to 40%, 20 to 40% here, or 0.2 to 0.4. Other important thing is the velocities. That is velocity at the tip of the paddle and velocity of the water adjacent to the paddles. What are they? So now what you see here, when the impeller is rotating with high velocity, so it will be having a velocity here, Vp. So maybe it is moving with some velocity in this direction. Let us assume this. That means in this direction. Paddles are moving in this direction. But water is there. Water always tries to oppose the movement in its way. So ultimately, so water will be moving in the opposite direction with some velocity. So water, when not the blade is moving, water is opposing here. So if you want to, blade should move continuously forward, it will have an effective velocity over and above the velocity of that particular water. So that's what we are calling as relative velocity, VR. It is nothing but difference of Vp and Vw. So normally we are taking it as equals to 75% of the paddle velocity. That means we are assuming that the friction due to water in the opposite direction for the movement of velocity of the paddles is 25%. So remaining 75% is nothing but the relative velocity. And another one is because the object is moving in a immersed fluid, so you will have a drag force, and then the drag force is again because this is move, the impeller is moving with some rotational diameter and velocity. So we are having a force related to drag force. The power is there. Power is also calculated force into lever arm. The drag force into lever arm we are going to calculate, which is equals to half CD A rho V rho nothing but rho W VRQ. What are these things? So A is nothing but area of the paddles, effective area of the paddles. Okay. And rho W is nothing but the density of the fluid. We are talking about water, say 1000 kg per meter cube. And VR is the relative velocity, which is nothing but 75% of paddle velocity. And CD is the coefficient of drag and depends on the machine manufacturer, the impeller, whatever is there. So this manufactured data we will going to take as a constant value. And P is nothing but the power induced here using the relation we already calculated, G square V mu. That value we are going to use, and subsequently we are going to calculate the area of the paddles. Once you have the area of the paddles, number of paddles, you can assume 2, 4, 6. Accordingly, we will go for the sizing of the paddles. We'll quickly look at the design parameters as well as the small example. So now you can see here, this is the uh, configuration of a flash mix chamber, and subsequently the design guidelines. The mean velocity gradient, which will be greater than 300 per second. We can take higher values also, but we have to have a check every time. Even higher values sometimes may not be suitable as per the design criteria. So P is equal to G square V mu. G square V mu is what discussed. The residence time or detention time is 20 to 60 seconds. The rotational speed of the impeller, which will be around 40 to 140 RPM. We try to keep it higher than 100 RPM. 20 to 40% is the ratio of the impeller to tank diameter. Usually we go for a circular configuration of the tank. And H by B, as I said, height is more than the width or diameter, 1 to 3. And subsequently, what you are going to see in this is power requirements. You have to have a check. How you are going to check here? How you are going to check? You can see 1 to 3 watt per meter cube per hour of flow. 1 to 3 watt per meter cube per hour of flow. Then the tangential velocity, that is nothing but Vp, the paddle velocity, a tangential velocity Vp, it should be greater than 3 meters per second. And the power input to the impeller is based on the drag force, half CD A rho VRQ, and VR is nothing but 75% of the paddle velocity. Let's quickly take a simple problem. Let's quickly take a simple problem here, and then we'll calculate 300 meter cube per hour of water is is to be used in a tank, and you design a flash mix chamber for that. The temperature of the water is 20 centigrade. First of all, we have to go for sizing of the tank. To have a sizing, we need volume. When you need a volume, you need to have the detention time. Discharge is known, time is known, you can calculate the volume. Detention time multiplied by discharge. Here, meter cube per hour is there, time is in seconds. So, converting the meter cube per hour into seconds, I'm getting 2.5 meter cube is the volume. Once you know the volume, you have to identify the size, shape of the configuration, the tank flash mixer. So I'm assuming a circular one. So volume will be equal to pi by 4 d square into h. Pi by 4 d square h I'm going to calculate here, which is equal to 2.4 meter cube. So here what are unknown as d and h both are unknown. So we know the relation between h and d. H by d is equal to 1 to 3. I'm assuming h by d is equal to 1.5. So h is equal to 1.5 times d. So subsequently substituting back and calculating d is equal to 1.3 meters, h is equal to 1.59 meters, and small freeboard I'm adding 20 centimeters. So total depth of the tank will be around 2.15 meters. So once you calculate the volume and diameters, now we'll go for power consumption or requirements in the flash mixer. We are having the formula P is equal to G square V mu. P is equal to G square V mu. We are having this value. So now volume of the tank is known to us and temperature of the water is known. So then we will be knowing what is the absolute viscosity at 20 centigrade. So that is equals to 1 in 10 to the power of minus 3 at 20 centigrade of water. Then G we have to assume 300 per second is the limit. You can go higher values. I'm assuming 600 per second, and subsequently I'm calculating as equal to 908 watts of power. 908 watts of power. So I can calculate, I can assume any other value, doesn't matter. 600%, 400, 500, 600, anything is there. But ultimately, we should have a check. This check should be satisfied. Then only what are the assumed value that will be holding good. Power per unit flow of water, the total power required divided by 300 meter cube per hour, which is around 3 watt per cubic meter per hour. So that is within the range. So it is okay. Now let us go for the sizing of the blades and impellers. Okay, so now we are having a diameter of impeller to diameter of the tank 20 to 40%. I'm assuming 40% diameter of the tank. Since the diameter of the tank, that is a capital D, is known to us. So diameter of the impeller, say this is your small d. So 0.4 times the diameter, which is 1.3 into 4, 0.452 meters is there. So in the range of rotational speed 40 to 140 RPM, I'm going for 125 RPM here. So velocity at the tip of the impeller is a 2 pi Rn by 60, because this is given in RPM, meters, minutes. So it should be converted to seconds by dividing by 60 here. So radius of the impeller with nothing but the half of the diameter, 0.452 by 2, 0.226. So V is equal to 2 pi Rn, 3.4 meters per second is greater than 3 meters per second. So this is also all right for us. What next? We have to calculate the size of the bladings. So size of the blades, how to calculate? First of all, we should know the relative velocity. Relative velocity is nothing but 75% of the paddle velocity. Paddle velocity already calculated 3.4. 75% of that is 2.55 meter per second. So we are having the formula for power requirement using a drag force half CD A rho VRQ. VR already calculated 2.55 now. density is water, so 1000 kg per meter cube. Power, already calculated 908 watts requirement. CD is a constant, so that is from the manufacturer of the machine. So now you can have as a 1.8 a standard value. From that, we calculate the area of the paddles, blades, area of the blades. Now, how many number of blades are there? Once we have this area, now we can have a number of blades. You can have 6 blades, 4 blades, 3 blades, 2 blades. So the area of the blades should not be too large for distribution point of view. So based on that, you calculate the area of each blade and then put some sizing here. For simplicity, I have taken 6 blades. So it is 9 centimeters versus 12 centimeters. Suppose even if I take 4 blades, it will be around 0.015 meter square. It will be around 150, 1500 meter square. So 150 centimeter square. 150 centimeter square means I can have 10 centimeters into 15 centimeters sizing of 4 blades. That is sufficient for this flash mixer. So we can have 6 blades, 4 blades depending on availability and for convenience. So this completes the design of flash mix chamber. The next video we'll go for the design of flocculator, which is the second part of the unit operation for coagulation practices, right?